So now it's the most mind-blowing data structure in, I think, in the mapping worlds. It's called Burrows-Wheeler transform and LF mapping. This data structure is used in the two tools probably you will use quite often later is BWT and BWT. And you can see their citation numbers and the year of their publications. They already has in more than 20,000 citations for each tool. And here is the general framework for how to use the Burrows-Wheeler index. Is first way for the human genome, we just first concatenate that into a very big genome, and we just use the transform to build the index. And for each query, for each read, when you search in the index, we will see how it done before, and it also allows some. It will use like backtrace search to allow some mismatch in the search. We will see that later. And here there are some videos. So first, let's look at what is the Burrows-Wheeler transform. So this idea was first used not related to bioinformatics. It was first used to as a compression algorithm. That is like bzip is based on the Burrows-Wheeler transform. For example, for our reference genome, it's looked like this. First, for each suffix, we write out the remaining part of the genome so we can form a like the rectangle matrix. And then we order the suffix, just like how we build suffix array. And this matrix is called Burrows-Wheeler matrix. And it can be built from using the suffix array. And we are most interested in the last column, and we will see why. And the result of the transform is that we only need the information of the last column. And based on the last column, we can reconstruct the original sequence, and we can also do the mapping and the other magical stuff. So first, let's think why Burrows-Wheeler transform is very useful for compression. So first, the length of itself is the same as the original sequence, so we did not add any stuff. And also, after the sorting, there are some very beautiful stuff. Like if we are compress English literature, there are many words like the, the, and when we sort in the suffix, all the sentence, all the suffix starts with the will come together in the Burrows-Wheeler matrix. And also all the words, like HE will also come together in the after we sorting.
So basically, if your data is completely random, from random number generator to get the ACGT, you don't really save much from the first one was next one. It only saves space because there are some repeating patterns.
Yeah. But for the bioinformatics too, it does not use that compression technique a lot. The most used for how it can be used to do the mapping with only the last column. That's what it's.
Like repeats the genome or codons that are repeated in the genome will be kind of together.
Yeah. But we only need this is like in the middle part. After the end of this particular, only this part. So that is the last column.
So is it like instead of having to store all the suffixes, you only need to store that thing at the end?
Yeah.
And then you can reconstruct the suffixes.
Yeah.
So that's what you say space.
You want to reconstruct the original sequence. And since like after rerouting, the last column is the
Actually, can you use your mouse?
yeah.
Otherwise,
Yeah.
people are video.
yeah, like like this one is the always the always the character before this one. Like if we are compressing the English literature, all these are all the HE and these are THE. So we will have a bunch of T coming together. See that relationship? And then we can use just a straightforward run length algorithm to compress. Like if there are 100 T's in the last column, we can just represent by T100 as something here. We can just use just 3A to represent 3A's. Yeah. But these are not quite relevant to the mapping. So first, let's see the magic part of the BWT transform, how to use that to recreate the reference genome. And then we will, after we get familiar the idea of LF mapping, then we can see how to use that to find the mapping, the coordinate of the read, the query, which you are interested in. So the most important idea behind Burrows-Wheeler transform is the LF mapping. That is the ith character in the last column corresponds to the ith occurrence of that character in the first column. Like, for example, for this A, it's the second A in the last column. There is only this A before that. And this A corresponds to this A. As you can see, this A is correspond to the 0 suffix in the string, ACAACG. And this A also correspond to the 0 suffix, ACAACG dollar. Why this is true is because when we look at the first column for these 3 A's, they are all sorted by suffix array. Since they start with the same nucleotide, they are actually sorted by they are actually affected by the character or nucleotides after that. Like they are actually sorted by this. So when we shift the first column to the last column, like to this suffix will stay. These 3 suffixes will stay the same order in the Burrows-Wheeler matrix. Like this ACG is this ACG is correspond to this one. This CAA correspond to this one, and this CG dollar is correspond to this one. They are in the same order. And that's why the LF mapping is correct. Any questions? So this is the most key idea in Burrows-Wheeler transform. And it's a bit confusing. So now let's see how we can use LF mapping to reconstruct the original genome by just using the last column of the, by just using the BWT. Then first step, since the dollar sign has the least lexicographic order. So it's the first column. So we can just directly know, we can just directly see the last character in the reference genome is G. Note that when we construct the genome, the order is from last to first. So it's also quite weird. And this G is the first G in the last column. So it will correspond to the first G in the first column. And for this row in the BWT, it's a character C. And this C is the second C in the, so we know the nucleotide before G is C, then we add that to the reference genome, constructing reference genome. And this C is the second C in the BWT. And then we go to the first column and see this, this C it corresponds to this C. And it's on this row in the BW matrix. And this and the nucleotide on that row in the BWT is nucleotide A. So we add A to the reference genome. And this A is the third A in the last column. So it corresponds to this A, the third A in the first column. And then we look at what's on the last column in that row, which is also A, and we add A to the reference genome. And this A is the first A in the last column, so it corresponds to this row. And the C is the last column on that row, and then we add C to the reference genome. And after that, we add A, and then we finally retrieve our original reference genome. We are just applying the LF mapping again and again, and we reconstruct the reference genome. Yes?
So then the overall goal is to rearrange the original sequence in a way that allows you to condense it without losing the original sequence information?
We can do that, but in bioinformatics, we are not doing comparison. We will see that how to just use the last column to do the alignment. But from the perspective of computer science, we can further condense the last column. But currently, we just see this procedure, just see using the last column alone, we don't lose any information. Yes?
How do you know that the third step of the odyssey?
You mean this step?
Oh,
This one?
yeah, so you went from the bottom, the last C, the column,
because this C, there are only one C before that. This C is before that, so this is the second C. And then we can see it's it corresponds to on this row. Yeah. So also I forgot to mention that we also use when we do the LF mapping, we also will tell like since the first column are already sorted, so they are all A's come together, and all C's are coming together. So we can just represent the first column by 4 integers, which says all the A's starts at that position, and all the C's start from that position. And then we can tell the second C start from the first C's position plus the rank of that C. And that number can be obtained by, if we don't want to store that 4 integers, that number can be obtained by just scanning the last column. Just count how many C's there, how many A's there. Yes?
So for every read, you have to put that termination signal onto that space $, and that allows you to provide starting.
Yeah, exactly. Yeah. Now let's come to the interesting part, how to use the BWT to retrieve the coordinate of the query. For example, our query is the AAC, and our reference genome is ACACG. After BWT transform, it looks like this. So first, also when we do the alignment, we also doing the steps from right to left. That is, for the query, we start from the last nucleotide and we move to before. Like for the last nucleotide C, we will know that all the it will pass all the suffix start with C are in this range, which we kind of pre-store that information with, because we only need one nucleotide information. And then we want to match A to this suffix. One way to that is for each entries in the range of C, we find out the rows that has A before that, and it has A in the last column, and we do LF mapping. Then we can know the suffix start with AC coordinate. Like for example, in this range for each C, we do this operation test check whether the last nucleotide is A or not. If it's A, then we do the LF mapping. Like for this one, it's the second A, so it corresponds to this. It will correspond to this row, and for this A, it corresponds to this row. And then we move to, that's how we move to the next nucleotide, the second last nucleotide. There are some there is one important tricks to speed up this procedure. We don't need to look at the entries in the range one by one, because so like imagine like this range is very long. So like this A is the second A. Then we are interested in the range will be the third A, the fourth A, and the fifth A. Well, after we do the LF mapping, in the first column, it will correspond to the second A, the third A, and the fourth A. It will also be a range. They are consecutive. So when we move the range, we only need to update the first A's in the range and the last A's in the range. We don't need to worry about like the third A, fourth A, and the fifth A. We only need to update the coordinate of the third A and like the 10th A. And after that, we will see this in this range is the suffix starts with the nucleotide AC. And in this range, we update the range again and see there is only one A in the BWT in this range. And we do update the top and the bottom pointers in the range, and it will give us only one interval of size 1. And after that, the query is aligned to the genome, and it starts in this position. So this step tells us AAC exists in the genome, and we still need to find out which coordinate this suffix comes from. This is kind of start in the middle of reconstruct the origin genome. Like we just do the LF mapping again and again until we reach the first nucleotide on the reference genome. And we can say this AAC is this AAC is the third, starts at position 2. Yeah, here is the procedure of retrieve the coordinate of that query. Of course, this this is very slow because we need to go through the reference genome back to the end. So in practice, people will store like a samples. If you still remember the suffix array, people will like store like this. People will store the suffix arrays number for this row, every second row. So when we do when we found the AAC, we know the C is before that, so we like extend the reference genome backwards. And for this AAC, when we do the LF mapping again, we will come to this position, and we like pre-store that information here. Like this is 7 something, and we will know we run like one step of LF mapping, and we know the coordinate of this suffix. So the coordinate of this suffix plus the number of ALF mapping we do is the coordinate of that query. Any questions? And there is one more trick in practice is I kind of did not mention in detail is how we know this A is the second A in the last column, since in the last column it's not ordered again. So people will also like sample like every 128 base pair, like there are this many of A's before that position. So when we need to know which this A is the second A, it just can start from this sampled count array and just start from there and say there is 1A after that. So it will be this 0 plus 1, and then we can tell this A is the second A. So that means in practice, instead of the BWT itself, people also put some other data structure along with that, so we can retrieve the coordinate of the query fast. But still, that is much memory efficient. For example, human genome, we can do that within 4 gig memory, which you can run alignment on your laptop. Any questions?